Hello, everyone. My name is Fazlić, and today I'm going to present you my PhD project titled Historical and Industrial Paints under Synchrotron Light. This project is founded as a collaboration between the European Synchrotron Radiation Facility as the host institution, Rijksmuseum and University of Amsterdam as academic partners, and AkzoNobel as the industrial collaborator. The project is funded by the Maria Skłodowska-Curie co-fund program called the InnovaXN. What is a synchrotron facility? I'm going to give you the example of the European Synchrotron Radiation Facility as the most intense source of synchrotron-generated light to shortly explain the synchrotron radiation to those of you who might not be familiar with it just yet. Electrons emitted by an electron gun are first accelerated in the linear accelerator and then into a circular accelerator known as the booster synchrotron, where they are accelerated to an energy of 6 billion electron volts before being injected into the large storage ring. When injected into the storage ring, which is 884 meters in circumference, they circle for hours close to the speed of light. As the electrons travel around the ring, they pass through different types of magnets, and in the process, they produce X-rays. These X-rays are then directed towards beamlines that surround the storage ring in the experimental hall. There are 41 operative beamlines, and each beamline is designed for use with a specific technique or for a specific type of research. ID 21 is one of those beamlines dedicated to different fields, including heritage science. Synchrotron-based techniques can be used within the heritage field to understand what are the components used to create the artwork and what are the physical and chemical reactions involved in the creation of the objects intentional by the artist and the ones present independently of his will, known to us as the degradation. These information are also important for the future preservation of the heritage. We can additionally obtain information on the authenticity of the object if a certain pigment was, for example, synthesized only from a certain date. The potential of the synchrotron-based techniques to analyze complex and heterogeneous paintings has been demonstrated for years. For example, the degradation of chrome yellows in Van Gogh's Sunflowers, the chemistry of cadmium sulfides of the Scream by Munch, 3 portraits by Rembrandt to study his impasto, and the fragments from Buddhist mural paintings from Afghanistan. Now, I would like to give you a more detailed example of one scientific study which illustrates the use of synchrotron techniques and methods applied to cultural heritage object analysis. The object in question is an anonymous portrait from the 17th century. The starting point of this research was the restoration of the painting, which was exhibiting numerous protrusions of unknown origin. The first step of the research was the observation by visible light microscopy and scanning electron microscopy. Based on the acquired images, which you can see on the right, it was possible to conclude that the lead is present as a pigment, in particular in light areas in the surface, as a cicative, diffusely distributed in the ground layer, and as protrusions located in rather internal regions. To understand the composition and origin of the aforementioned protrusions, further analyses were performed at the ESRF, such as mFTIR and mXRF. Based on the elemental maps, which are shown here on the slide, and the spectra that was acquired, it was possible to report the presence of carboxylates and lead in the ground layers. After proving that the protrusions are indeed the lead soaps, The main objective was to understand if they come from lead, introduced as a seccative to inhibit the drying reactions of the painted layers. For this purpose, a reconstruction of the painted layers was done in the laboratory according to the information from the historical manuscripts. In a recipe by de Mayerne, huile de litharge was used, which is in fact prepared by cooking linseed or walnut oil and lead oxide together with some water on the fire. This mixture was particularly suitable at the time to prepare the ground layers. Reconstruction of this recipe revealed that it corresponds to the partial saponification of oil into lead soaps. And as you can see here on the right, the mock-up painting prepared using this huile de litharge revealed the formation of protrusions after only 1 month. mFTIR and mXRF mapping of 5-micron thin sections of the mock-up paint revealed that the protrusions are, once again, made of lead soaps. The same mock-up samples were revisited 9 years after the application, and they were analyzed with mXRD mapping. The pattern, which you can see on the slide, as well as the map, revealed that the lead soaps are still present, in this case as plumbonacrite, which, as you can see here in the red, is identified mainly in the protrusion, but also distributed in the matrix. The previous case study that has been presented to you has led my colleagues to develop the project that I am currently working on, which is focusing on the use of dryers. As you all know, the introduction of oil as the main binder revolutionized the art that we know now. Natural oils are mainly composed of unsaturated triglycerides. The unsaturated bonds of these fatty acids are fundamental to the drying process, since after breaking, they will allow the polymerization of the oil. The natural autooxidation process can be accelerated by the addition of metal catalysts or the so-called driers. There are 2 types of driers, the primary and the secondary ones, and they're usually combined. The first ones promote the oxygen uptake, the hydroperoxide formation, and the composition processes, whereas the secondary ones are said to enhance the cross-linking of the film and serve as the sacrificial metal. As you can see, different types of dryers have been used throughout the history. For example, in antiquity, lead was used as the primary dryer, while manganese and iron have been used as the secondary dryers. By the analysis of historical samples and the reconstruction of the historical recipes of these samples, our collaborator, Rijksmuseum, will be provided with a better understanding of the historical use or misuse of dryers in historical paints. Additionally, based on the information provided through this project, they will also obtain a deeper insight into the conservation issues, such as delamination, protrusions, wrinkling, or dripping. On the other hand, by the analysis of contemporary paints, which could contain cobalt, manganese, or iron as primary dryers, calcium or zirconium as secondary dryers, our industrial collaborator, AkzoNobel, will be able to design new paints with a better health and safety profile and an improved performance. This simple scheme illustrates how we study the interaction of the binder and the dryer on a microscopic level. What we have is the binder layer and the dryer particle deposited on it. What we expect to see is the reaction and then the diffusion of the dryer in the binder and eventually the formation of the onion-like heterogeneous structure around the dryer particle under different environmental conditions. The interaction of the binder and the dryer can be studied in 2D, so as thin sections which you have seen on the previous slides, or it can be in paint surface as it is demonstrated here. Once we have the region of interest, we can then analyze it with different synchrotron-based techniques, which were mentioned before, such as mFTIR, mXRF, micrograins, and mXRD mapping. Apart from revealing the information about the composition of the historical objects and their possible degradation products, synchrotron radiation itself can generate a certain type of alteration, which is known as radiation damage. Besides the study of the binder and the dryer interactions, we are also trying to understand how the radiation damage occurs, what type of reactions occur with exposure of the sample to the beam, and how it may be reduced for future characterization of historical samples, which, as you know, hold a great importance and should stay intact. Within the study, mXRD maps were acquired around the smaller areas of the sample in order to produce the radiation damage. Then, larger mFTIR maps were acquired around the irradiated area in order to understand what type of alterations occur with the exposure sample to the beam, but also to understand the extent of radiation damage by the comparison of the non-irradiated areas around here to the irradiated areas around here. On top of this, visible light microscopy was performed regularly in order to follow the visible alterations that might occur with the exposure of the sample to the beam. In the end, I would like to thank my supervisors as the co-authors of the project, as well as the INNOVA-XN doctoral program that supports the entire project. I would also like to inform you that it is possible to apply for beam time at the European Synchrotron Radiation Facility and use the aforementioned techniques for your research as well. Thank you very much for your attention,